A basketball game gives off endless amounts of data. Cameras from all angles capture the players making their way around the court, dribbling, passing, and shooting. With computer vision, a computer can build a well-defined understanding for what a basketball game looks like, or what any sport looks like. With other machine learning techniques, the computer can make predictions by combining historical data with a game that's going on right now. Second Spectrum is a company that builds products for analyzing sports. At major basketball arenas, Second Spectrum cameras sit high above the court, recording the game and feeding that information to the cloud. Second Spectrum's servers crunch on the raw data, processing it through computer vision and putting it into deep learning models. The output can be utilized by teams and coaches and fans. Chang and Jeff Su are co-founders of Second Spectrum. They joined the show to describe the data pipeline of Second Spectrum, from the cameras on the basketball court to the entertaining visualizations that are the end result of all the work that they're putting into this company. After talking to them, I'm convinced that machine learning completely changes how sports are played. And it's probably going to open up a platform for how new sports are even invented in the future. You can imagine things like augmented reality glasses or contact lenses really changing the type of sports that could be played. If you want a better way to listen to Software Engineering Daily, check out our apps for iOS and Android. These are the first projects to come out of the Software Engineering Daily open source ecosystem, which you can find at github.com/softwareengineeringdaily. The mobile apps make it easy to search for episodes, to get recommendations for episodes, and it provides a great index for the 600 episodes of Software Engineering Daily. If you want to help build a better Software Engineering Daily experience, check out github.com/softwareengineeringdaily. We're working on this Android app, this iOS app. We're working on a back-end recommendation system. We're working on a web front end. All of these things are working towards building a better way to consume content about software engineering. And we'd love to get your effort into it if you are interested in contributing. So you can always send me an email, jeff@softwareengineeringdaily.com, or again, check out github.com/softwareengineeringdaily, or check out the apps. With that, let's get on with this episode. Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar. SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Writely is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast. And you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR. softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily. Yuhan Chang and Jeff Su are co-founders of Second Spectrum. Guys, welcome to Software Engineering Daily.
Thanks for having us.
So Second Spectrum makes sports analytics tools. And before we dive into the engineering of how that works, let's start at a high level. So let's take a basketball game. What are the pieces of data that you could record from a single basketball game that could be turned into useful insights?
Yeah, so essentially what we've been able to do is get a computer to watch a basketball game and kind of break down what's happening on the court the same way that, a professional NBA coach sitting on the sidelines would see the game, right? So this goes down to fairly sophisticated actions and sort of plays that are happening on the court. So if you think about it, it's not just that this guy is dribbling the ball down the court. He's making a pass, there's a touch, there's a possession, there's a shot. We also are able to get the machine to automatically identify, okay, they're running a high pick and roll. The defense is switching in order to react to that pick and roll. We're able to look at off-ball screens, look at a dozen different ways that a team might run an off-ball screen and all the different ways that the defense then reacts to it, right? So this is a fairly sort of deep way of looking at the game, and we're getting a machine to automatically watch that game using cameras and computer vision and break all that down so that it knows exactly what happens in each and every moment of the game. Now, what that enables coaches to do is that now if they want to pull up video for anything that happened in any game in the NBA over the last 3-4 years, they just type in a query, click a few buttons, and they have it, right? And this has really been groundbreaking for both the coaching staff, the video coordinators, as well as the front office, because it's almost like a magical search tool on video now. They can click a few buttons and bring up any sort of very detailed query or thing that they have in their mind and they want to ask the computer, and they can get video immediately for it.
Let's start with the data at the creation point. So on the basketball court, do you need some kind of thing that's collecting data, or is all of the data processing just done from computer vision on the video recording of a basketball game?
Yeah, it's a great question. So right now, there's a lot of different ways that we can do it. The way that we've chosen to implement our system, and it's currently deployed in all 29 arenas around the NBA, is that we have cameras mounted in the rafters of each of the arenas. So these are 10 cameras pointed down, watching the game happening down below on the court. And that's essentially the signal from which we're able to do all this other work. Now, we bring in other pieces of data and information, for example, from the play-by-play and box score and stuff like that, to correlate it with the frames of video that are coming in from the cameras, but essentially it's all being done from the video. The computer is just watching what's happening in all of the cameras and is able to deduce all the things that we were just talking about.
So the cameras are the main source of information, or do you cross-reference that with live video streams from ESPN or something? So
that's an interesting aspect to the work, right? So right now, Second Spectrum has been providing sort of coaching tools for the NBA teams for the last 4 years. And most of the teams in the NBA use our system in their organizations. Recently, we've actually been starting to look at how this translates to making a better fan experience, and sort of how this translates to a person at home watching the game and how it can benefit them. And so for that experience, we're actually looking at different kinds of video, like what you mentioned, the broadcast video, sort of what ESPN or Fox would put on the air. And we're able to integrate that view of the game together with the computer's understanding of the game, and really create a different kind of experience there as well.
Since you've been focusing on the overhead camera data, which is better structured data, let's just focus on that for a while. I'd love to know the data engineering pipeline for, you've got these overhead cameras that are just recording data of a game. how does that make its way through a data engineering pipeline that aggregates and stores and processes the data?
Yeah, so currently what we have is we have these machines in every arena. And so the cameras feed the machine, they're IP cameras, and they feed machines the raw imagery. And then through that, we send that to the cloud in AWS. And then in AWS, we have a bunch of machines that kind of process all those cameras in sync, triangulate a bunch of things, run that through computer vision. And then that converts essentially all that video into coordinates, right? And then we take those coordinates, we feed it through our what we call our semantic layer, which is essentially spatial temporal pattern recognition. So those coordinates are the inputs, and the outputs we get pick and rolls, we get like basically different plays, shot probabilities, and all of that, right? Then we feed all that data into sort of your different databases depending on how we want to query it. And then that, essentially the apps that the coaches we use, the suite of tools, they'll all query the databases in different ways.
So help me understand a little bit better that the beginning stages of the pipeline, when the video data is just coming in, are you queuing it up on Kafka or something, or are you just, I guess you could just take one long video stream and then process it afterwards. Like, I mean, I'm just curious if you need to do something in real time, like if you need to take in the video data in real time, or if you can just batch the entire video file at the end and then do all the post-processing.
Oh, we take it in, I guess, pseudo real time. We currently upload around 4-second chunks of video, and that gets queued into Rabbit, and then that goes through. We have a process, what we call a decider, which kind of takes all these messages and syncs them up. Because currently, unlike a standard DAG, we need to sync up all the cameras, right? So in order to get like coordinate information, we need information from 10 different things at the same time. So we have a separate process that kind of unifies all the messages we get and organizes that so that we can run our computer vision algorithms against it.
Talk a little bit more about that. So you've got these 4-second chunks that are coming in, they're getting queued up, and you need to have deciders run on them. You need to synchronize them somehow. Give me a better picture for how those 4-second chunks get integrated into a holistic view.
Right. So currently, it all resides in one process, or it's multiple processes, but they're all backups. So essentially, there's one and we save the state in. So if that goes down, another one will pick it up. But that thing, because of the nature of how the data is coming in, the videos kind of come in around the same time. So we receive these messages, we buffer them in this process, and then we kind of align them as they come in, if that makes sense.
Yeah,
so
no, it makes sense.
So it's like a zipper almost, right? And then we re-queue them onto Rabbit, and then now we have this nice, clean workflow that behaves more like a traditional DAG.
Now, once you have that zipped up view, what are you doing on the fly to that video content?
So that's where the next step is really feeding it through our computer vision pipeline, right? And the best way to think about how that works in terms of our full stack is I often compare it to, in the early days when people were starting to do things like machine understanding, AI, machine learning on content. Google really did the first version of that on the web, where they were able to scrape a bunch of text data from the web and then provide some layer of semantic understanding on top of that scraped textual data to give people a way to search through it, right? And essentially what we've been able to do is use the computer vision layer to do the scraping of video, right? So we have a lot of video coming in that's kind of like all this text out there that a computer did not know anything about, and there needs to be a way to scrape it. So the computer vision essentially does that scraping where from that video, now we have X, Y, Z coordinates of the players and the ball at 25 frames a second throughout every single game, right? And then that's what gets then fed into the semantic layer that gives that semantic understanding on top of it and says what's actually happening so that a coach or a front office staff can query it. Now, the computer vision pipeline, one of the great things about the way we've architected it is that, since the video gets directly streamed up into the cloud, it can then be distributed to any number of, worker machines up in the cloud, and we're able to parallelize a lot of those processes. And that's exactly what we're doing, right? So, every frame of the video goes through many steps of, sort of our computer vision stack. And the result of that is really these tracks. So player coordinates, ball coordinates at 25 frames a second. That's the output of the computer vision that then gets, fed further down the pipeline.
You have a software project that you want to build. Everybody does. I love building products, but I know more about how software fits together than how to actually write the code itself. I don't spend a lot of time writing code, but I do like to build software. That's why I use TopTow. TopTow is the best place to find reasonably priced, extremely talented software engineers to build your projects from scratch. You can get a pair of Apple AirPods when you use TopTow.com/SEDaily to work with an engineer for at least 20 hours. And I recommend it. I think it's a great way to build your projects if you don't have time to build them yourself. There's a misconception that engineers have to build all of their own projects just because they're capable of doing that. It's not true. TopTow has only the top 3% of developers. They turn away 97% of the developers that apply to work on the TopTow platform, and that's how you get a matching process that's unlike anything else I have seen in the freelancer marketplace. And I've tried a lot of different freelancing platforms. TopTow has such high-quality engineers, and they listen through the design specifications that you have. They handpick the perfect developer for your project, and this has saved me countless hours in my development process. There's really nothing that compares to TopTow that I have seen. So you can get a free pair of Apple AirPods when you try TopTow at TopTow.com/SEDaily. Find an engineer that's going to help you build your side project and get your MVP off the ground. As long as you do at least 20 hours, you get those free Apple AirPods. And if you've already got a company that you're working on, you can also use TopTow to scale your team and get everything done faster and raise the bar for your engineering, or get through that blocker that's preventing your company from getting to the next level. So check out TopTow.com/SEDaily and find an engineer who will help your project succeed. Well, let's go deeper into the computer vision aspect of it. So let's say we've got a video. We want to track players and track the ball as they move through the court. What are the computer vision algorithms that are needed for that process?
So it's actually a combination of a lot of different things, right? And I think that combination of ways of looking at the problem is what allows us to get a very high degree of accuracy that hasn't been achieved before by other companies who have tried to do this. And then sort of the ability to do all this processing in the cloud is what enables us to do it really, really fast, right? So I think other people who have tried to do this have either tried to do it locally on a couple of servers in a stadium, for example. That's both not as accurate and not as fast. But what we're able to do is, through the video ingestion and uploading it into the cloud, now all of a sudden we have essentially unlimited firepower to throw at this problem, right? And so unlike other approaches, we're able to essentially throw, you can think of it as the kitchen sink of computer vision algorithms at it, right? And run them all simultaneously in order to improve that output that comes out so that it's as accurate and as fast as possible.
Well, so what are some of the ways that computer vision has changed recently, or has gotten really good in recent years, to make this domain really accessible?
Sure. And one of the things that has happened recently, and I'm sure most of your listeners, have read a lot about this, is, the deep learning stuff that's come out has really helped to make a lot of the machine learning and computer vision work a lot easier, right? And so we're also using a lot of that technology in order to train the machine to understand, for example, objects and actions in the game very easily and very accurately, and that's part of the pipeline, for example, right? So there's a lot of different ways of doing this, which is why earlier I was referencing the fact that you can throw a lot of different techniques at it and have them layer upon each other in order to improve the performance. But the deep learning aspect is certainly one of the key components where, for example, you can have a machine look at the court, identify the faces of the players, identify the figures on there. Here's a person, here's their head, here's parts of their body, here's the ball. Those things are essentially nowadays not very easy to do, but very accessible for engineers to get a handle on when they're looking at problems like this.
Could you describe a model that you've built from the point of view, like describe some of the layers that would go into a given model and the features that you are training on?
So, I think the nice thing about a lot of these techniques is that, you're able to get a lot of progress without necessarily having to fine-tune the features a lot, although certainly one of the things that we bring to the table, especially in the semantic layer and the machine understanding that goes on there, is the domain knowledge of basketball, right? And where once the video has been processed and is actually a bunch of XYZ coordinates, that's where a lot of the understanding of the game of basketball or the game of soccer, we've been doing a lot of work in other sports these days, in soccer and in the NFL, other places, where the domain knowledge really helps and where being able to think about what's important and sort of understand the kind of features and the layers that go into the model make a big benefit.
Can you go into a little more detail on a specific model and describe how you architected it?
So let me think of a good example.
So one example I saw there was a TED talk that your CEO gave about your system being able to identify when a pick and roll takes place. So I can imagine that the process of building a model to identify a pick and roll involves getting a huge labeled data set and labeling a bunch of... First of all, you have to figure out how to label all those pick and rolls. So you would take a bunch of videos of picks and rolls taking place and get those labeled accurately. So like labeling that's a separate question I'm curious about. But once you have that labeled data set, you can say, okay, we've got 1,000 takes of pick and rolls identified. We're going to train our system on 500 of them, and then we're going to use the next 500 as testing data to make sure that they're being identified correctly. So I know that's kind of the high level description, but maybe you could motivate the example a little bit further by describing how the nitty-gritty of that training model might take place.
Sure. The pick and roll example is a pretty good one. And sort of how you talk through it is also fairly accurate. I think one of the things that we've done that's essentially part of our secret sauce is that we're able to do that kind of training for something that's as complicated as a pick and roll, which is this fancy dance between four different players on the court with a lot of subtle variations to it. We're able to identify that with a high degree of accuracy without actually having to label the enormously large data set that you were referencing, right? And so, that's part of our secret sauce that, I wouldn't want to get into in that much more detail. But the part of it where, you're training the model in terms of thinking about what features are important and being able to, build your model around that. I mean, I think those are techniques that, most people are familiar with, where if you're able to be somewhat thoughtful about it, say, think about what kind of things might be important for a pick and roll and apply your knowledge of the game of basketball to come up with any number of features that you want, right? I mean, there could be thousands of features that you come up with, whether it's speed, distance, the combination of distances between different players, where the ball is, these kind of spatial temporal markers, if you will. That's the library of essentially features that the machine is going to be looking at. And from that, we're able to learn a pretty good model using very few samples, and then iterate with the coaches so that, after talking to the coaches and, taking their feedback and bringing it back into the machine learning framework, a few iterations of that comes out with a very, very accurate model in the end, right? And so that's one of the benefits from where we sit, is that ability to go back and forth between us and the professional coaches in the NBA and really benefit from their expertise of like, okay, here's what the machine thinks today, given what you've told us so far. Like, tell us, what's right, what's wrong, and then let the machine kind of chew on that for another iteration in order to, learn from its mistakes essentially and get better at it. And so that's the system that we built sort of early on here. And now we're actually able to build on top of that and do a lot of other things where, we're combining the computer vision with this semantic layer to, do other things with that.
Okay, so I want to get a little bit higher level in a sec, but and maybe you can't talk about this at all, but I really am curious about this labeling aspect. So if you've got the entire corpus of video of basketball historically, and you want to label all the pick and rolls, one of the problems that your CEO touched on in that TED Talk video that I saw is that what constitutes a pick and roll is somewhat subjective. So, if you want to build a resilient data labeling pipeline, you need to have some way to attack that subjectivity. So if the question is, if you need to label your data and you need to decide, is this play a pick and roll or is it not a pick and roll? In order to get a good labeling, you might need to show that same play to 3 different humans, like Mechanical Turk type of people, and ask them, hey, is this a pick and roll or no? And you just take the answer from 2 out of 3 Turks, and that is how you can scale up a data labeling pipeline. But then that would mean that you need like this huge volume of Mechanical Turks that are familiar with basketball enough to identify the pick and roll. So is this an area that you could talk about a little bit more, this data labeling process?
So it's definitely a fascinating question. And, one of the things that I'll share with you is that when you go ask, the professionals, right? So staff on the teams, they will have different opinions on what constitutes some of these actions, right? I mean, I think most people will agree on the majority of pick and rolls, but there's some borderline cases. Some people say, yeah, that's a pick and roll, or that's not a pick and roll, or this is really an up to touch or not an up to touch. And, there's going to be disagreement even among the professionals. And so when we measure our accuracy of our algorithms, it's really fascinating to me that oftentimes what happens is that the level of agreement between our output and, sort of one of the coaches will be as high as or even better than sort of one of the coaches with a different team's coach, or maybe even the same team's coach. I haven't seen that happen, but certainly with a different team's coach, right? Because they just have slightly different ways of looking at the game and, different thresholds for what they would consider one action or not, or a different action. So that's certainly something that we've had to grapple with in terms of designing the system and, designing how we refine that process. But, that process really does involve kind of doing the labeling with the professional coaching staff at the teams, getting their inputs, feeding that through our machine learning pipeline, and then kind of iterating with those staffs. And, that's essentially how we end up with the high accuracy that we're able to achieve.
Okay, well, can you talk more about that iteration cycle, that feedback loop between yourself and, well, I guess your team of engineers and the coaches who are actually using this? Actually, before we do that, describe in a little more detail how a coach is making use of Second Spectrum. And, I think we might have glossed over this, but maybe just describe, like, if a coach is using Second Spectrum, what are they seeing? How are they interfacing with the Second Spectrum product?
Sure. And that's one of the things that's been really fascinating for us to watch, right? So I think we found this out very early, but, earlier I was describing that what we've built is essentially this machine that can watch the game, and the machine can understand what's happening at every moment of the game. And I think the critical thing that all the coaches and the players and the other staff at each team want from that is the ability to find video that they care about, right? I mean, there's a lot of analytics, a lot of data that goes into the system. And certainly there's people who care about that, right? They want to be able to count the numbers, see the statistics, find the reports on that. But one of the key things is being able to use that machine understanding to just retrieve video that they care about, right? So there's, prior to our system being in place, there was no way for a coach to just say, hey, we're playing the Warriors next week. Can you bring up, every time Steph Curry and Draymond Green ran a high pick and roll and the defense tried to trap them, what happened? Show me the video for that. I mean, there was a way for teams to get that video. They would tell their video coordinators to go find it, and then the video coordinators would spend, hours or days going through the last, 20 games of the season and trying to pull out those examples, right? And now we've shrunk that laborious process that only resulted in getting the examples from, the last set of, let's say, 20 games to 4 clicks, and you've got the 1,000 times that happened over the last 2 years, right? And so I think that's been really the key way that, sort of throughout the team's organizations that they use our tools. Now, the other part of that is really, in addition to the video, you have so much data, right? So if you want to see what's the best way to cover that high pick and roll, or what do most people do, and what are the outcomes, all of that is now identified by the computer, and you get tables and reports and histograms and ways of looking at that. So if you're a little bit more data savvy, you can use all that data to think about a hypothesis, come up with a hypothesis, validate that by looking through all that data that we present essentially on our, it's basically a website that they can log into, and then there's a lot of tools on there that they can dive into this data, but they can validate their hypotheses or come up with new ones. And then the key thing is that once the data analysts on the teams figure out something that they think can help their team win, they have the video at their fingertips, and that's key for them, because when they go and talk to the coaching staff wants to see the actual video, right? I mean, they certainly like the numbers, they understand the numbers, but in order to put full faith and trust that, hey, this is how we're going to execute in the next game, this is how we're going to win the championship game, they want to see the video. And so now we've empowered both the coaches to go directly to the video as well as the data analysts to, find these key nuggets and then back up what they say with the video. And so that, that's how the teams really get a lot of value out of this.
Got it. And what's the feedback loop between you and those teams?
So we work really closely with them, and this is really how I think we've been successful as a company, is that from the moment the company was founded, it was really an interaction between us and our early clients to figure out what they wanted and what could be most valuable to them. And that's actually how we figured out that video was such a key thing, because honestly, the first version of our product was a bunch of data reports and tables and histograms and data visualizations, which was great for a few people on those teams. But pretty soon, sort of within the first year, we found that, it has such a much wider applicability in every organization if we just add the video to it. So like everything that's on the site, if you look at a table, you look at a data visualization, now it links to video. And that was one of the examples of this feedback loop with the teams. It's like, they told us, like, yeah, the coaches want to see the video. And we said, all right, we can do that.
Square is a complete omni-channel payments ecosystem where developers can create a powerful commerce solution. You've seen Square around at your favorite coffee shops and retailers, and it's trusted by millions of businesses for its simplicity and reliability. But as a developer, you can unlock the potential of a full payments and business management platform with Square's APIs at softwareengineeringdaily.com/Square. There are APIs for online payments, taking in-person payments with Square hardware through a custom app that you build, and even inventory and employee management and sales reporting. Businesses of all sizes use Square's APIs to take payments securely online, in-store, and on the go with a single solution, and integrate with back-end systems that they already use. Check out Square's developer portal for all the tools that you need to get started today. Take Square's commerce solutions beyond the coffee shop and power payments for any type of business by going to softwareengineeringdaily.com/Square. It's a really flexible platform for building a business with payments and everything else that you need to get started with a business. And you can check it out at softwareengineeringdaily.com/square. That's softwareengineeringdaily.com/square, and it would support Software Engineering Daily. So thank you, Square, to being a new sponsor of Software Engineering Daily. Interesting. So give me a better picture for the infrastructure. I think really the only tool that we've touched on at this point is RabbitMQ, which is, kind of trivial in the scheme of things compared to your other infrastructure. Give me a deeper understanding for the cloud services you're using, the machine learning framework you're using, the database you're using. Let's get into the engineering.
Okay, so, like I said, we're on AWS right now. We run Nomad kind of as our base layer for deploying Dockers. On top of that, for our machine learning stack, we use a lot of Python. We optimize in C++. And we use the standard, scikit-learn, NumPy, pandas, and all of that for most of our machine learning and computer vision. And then on top of that, we kind of have a variety of technologies that we like to use. Most of our fast language processes are written in Go. And then we also use Elixir and Phoenix to sort of handle a lot of distributed coordination. And then on the front end, we were mostly on React, and then now all of our new stuff we try to do in Elm. Basically, because now we're getting into fan experience and not just building products for coaches, kind of the bar for the quality in terms of presentation for our products has been a lot higher. So, we have game developers here as well and working in C++ to build a game engine to kind of transform the fan experience. So really, in terms of going up and down the stack, I could talk about it for days because we just have so many different things going on.
Sure. Okay, so we'll explore as much of it as we can. I really want to get a better picture for that data ingestion pipeline and the machine learning pipeline and the database choices. Tell me about how you are storing that video data, and I guess prior to it being stored, what other kinds of transforms and metadata pulling you're doing from all that video data that's coming in.
Right. So, we use a lot of S3 to store a lot of intermediate data between the processes. So they kind of use S3 as a shared database. We're working on a caching layer for that to kind of speed up the I/O on that. But really the bottleneck right now is the algorithms, right? And as soon as we speed up those algorithms, we can start tightening up the I/O. In terms of the pipeline, outside of Rabbit, Postgres, and S3, that's pretty much, and Redis for caching, that's pretty much where the state of the pipeline is stored in. We kind of lean very heavily on storing things in process and then kind of saving them in Redis just for performance reasons, because we have very specific needs in terms of our data processing. Because like most data processing, it's like you have one piece of data and then that kind of flows through a DAG. For us, it's just there's a lot of dependency tracking that we have to do. For instance, we get play-by-play data from the NBA, right? So, and that kind of helps refine some of our output because we know, okay, a shot was taken here. So if we're not detecting a shot here, it's probably wrong. So we align a lot of our algorithms with outside data. So there's not really a kind of standard pipeline that we could apply to this. Because we're getting chunked video, we're getting kind of batch data from play-by-play, we're getting clock feeds from the NBA that may or may not be there because they're UDP and they're not guaranteed to be delivered. And so to resolve all that, all the data dependencies is kind of a tough problem for us building the pipeline.
You've mentioned this DAG a couple times. Can you describe in more detail what you mean by that?
So directed acyclic graph. So basically, the pipeline looks like this, right? A piece of video comes in, and then that piece of video gets translated into, several other things. Like it might be, we might transform the video color, for instance, for a machine to be able to detect something in that video. Or we might translate that into a series of images for whatever reason, so then we can parallelize some of the features that we want to detect in each frame. And then that all has to get stitched together into another process that kind of takes all that data, now no longer video, and spit out like a series of coordinates. So the data that comes through each part of each node in the DAG can be very different than the input of that node.
Sorry, say that again?
So like if a video is 1 unit of work in the DAG, that could translate into, multiple units because we split it up into images, right? So 1 unit of work can end up being 120 units of work to one part of the DAG, and then the other part of the DAG, there might be a 1-to-1 or there might be a many-to-1, just because we're dealing with temporal data, right? So like one video might map to 3 events in play-by-play, right? Wow. And so it's, there's this whole like temporal aspect of coordinating how the work flows through our data pipeline. So it's not your standard, like, here's a bunch of log files, process them, aggregate them, and then put them in a SQL database. Like, you can imagine, here's a log file, and each line in the log file is another intensive piece of work that has to be done, and then stitched together by another worker. So it's fairly complicated, and that's why we pretty much couldn't use your off-the-shelf database or off-the-shelf kind of data pipeline to solve this. We needed some in-memory processes to kind of handle that. Now, we've recently, for part of this DAG, we've leveraged Postgres a lot and used a lot of stored procedures to kind of handle the coordination of that. But that part happens later in the DAG when data isn't coming in as quickly. So we don't need to handle as many requests per second. But it's easier to use Postgres there.
It's a pretty unique data processing pipeline, at least given the different company. I've talked to a lot of different companies, and it's pretty unique. Did you get there through trial and error? Was there a lot of like mistakes along the way? Give me a picture for how you evolved to that data ingestion pipeline.
Yeah, I mean, there was a lot of trial and error. A lot of it is because we were ingesting data from other entities. So, we had, for instance, before we had 2 sources of play-by-play, we had broadcast video that may or may not have clock feed data. We have videos coming in from the stadiums from our own cameras, of which, some could be out and some, could be showing just errored frames. So it was a learning process, and we've started building something simple at first, and then as we encountered problems, we were always open to sort of re-engineering for that problem because we didn't know what problems we were going to come up or we were going to run up against. What we have today, I mean, honestly, the hardest part of building it is testing it, and because of the nature of this data, it only comes part of the year when the NBA season is on, and it has to work, right? So like there's no beta testing for this. So a lot of it is figuring out how to simulate noisy data, and we leverage a lot of like S3's versioning to kind of simulate inputs that come in at different times. And then we even introduce more noise than that to sort of make sure that our pipeline is robust.
Okay, so I just want to drill into something really interesting. You said there you use S3 versioning to do what exactly? So
for all of our inputs coming in, whether it's video or it's data from the NBA, we write to a versioned S3 bucket. And what that allows us to do is to know when this data came in. And when we want to simulate a real-world scenario, we can query S3 and kind of replay the events in which they happen. right, in which they occurred, or in the order in which they occurred, to kind of figure out, okay, this is kind of how it would behave in a real world scenario.
Yeah, I guess one of the differences probably between what we're doing and what a lot of people face is that we're processing all of this in real time and in an environment where a lot of the inputs are either unreliable or noisy. So it becomes very different if you just say, okay, we're only going to process stuff at the end of a game or like a few hours after the game when all the inputs have been QA'd, curated, they're all clean, and then we just run it through our pipeline, right? That would be way easier, and that's how most people do it, frankly. But, we want to do it in real time and have a process where, we're able to operate in this noisy environment. And then what Jeff was saying is that in order to test that process, what we have to do is to be able to replicate a real-time, noisy, unreliable environment. And so essentially what we're left doing is, trying to record what it looks like during one of these actual, live runs where stuff is, coming in, and sometimes it's wrong, sometimes it's not there, etc., in order to be able to test our system and have it ready when, there's an actual game on.
And another thing, we also have to engineer the system so that we can react to unpredicted inputs, such as like if a team changes their jersey, it's Chinese New Year, and they have a Chinese New Year jersey, and our computer, our algorithms are fairly generic, but they might not be able to handle, for instance, that particular combination of colors or fonts that's small. And so we kind of have to be able to train the models while we're observing it and improving the data as we go. So we're going to see the first pass kind of be inaccurate and then be able to run a second pass on the data and get better data, which means now the consequences in that DAG is that now we have to replace all that data and it cascades work across the system.
All right. Well, I could drill deeper into that, but let's pop out of the stack a little bit and to talk about Elm a little bit. Your front end is built in Elm. That's really unusual. I did a number of shows. I think I did 1 or 2 shows about Elm a while ago. I haven't heard of a lot of people using it in production, but the people who I have talked to really like it. So Elm, for those who don't know, is this functional language. It's like it compiles to JavaScript, right? Or compiles to JavaScript and HTML?
Yeah, so it's a framework and a language combined. So you can think of it as JavaScript and React. The main features is that it's functional and it's type safe. So the combination of those two things really give you an extremely safe environment. And the creator of Elm, Evan Czaplicki, he's done a really good job in making sure that if you have any compile errors, they're reported in sort of a language that is very readable, that you can just understand the error. In fact, I've gotten errors where it said, hey, this should really be this. And I would just copy and paste that in, and and the compiler was right. So yeah, we started out building all of our applications in React, and I've been using React for about 4 years now, or 3 years. It served us well, but I realize with React as a project scales, and we definitely have a lot of small projects that we're working on, it becomes hard to sort of context switch into a new project. So I heard a lot about Elm before trying it out, and last year I just spent a weekend hacking away at it and realized this is kind of all I want to write in. It immediately became my favorite language, and I started evangelizing it to some of the other functional programming nerds at our company. And it turns out most people, once they give it a shot, it ends up being their favorite thing to write in. Where now I have people that are engineers that before didn't want to touch UI programming, now are like, hey, well, if it's in Elm, I'm game. And so that's been a really big win for us, because we've been known as sort of a machine learning data company for a while, and most of the people applying for our company want to work in that domain. And so it's been a little tough getting people to kind of say, well, hey, we need to surface this in a UI. Like, are you interested in working on it? Or finding engineers that are willing to work on it has been hard. So Elm's been a good bridge for them because, it's very pleasant to work in and, very easy to pick up if you're familiar with functional programming.
So can you give a little more contrast to Elm versus React? So, for example, I haven't written much React, but my understanding is that the ecosystem is pretty rich and it's very easy to find components and take components off the shelf or take packages off the shelf that are really easy to reuse because it's such a dense ecosystem. Elm is a little more sparse in terms of usage. Is that an issue at all? Or maybe you could talk more about the pros and cons of Elm versus React.
So that definitely is an issue. I mean, React has a very lush ecosystem, like you said. I think one thing that Elm has going for it is that things that are actually, let's take drag and drop, for instance. In React, you're probably going to get, 2 or 3 major drag and drop solutions that you could deploy. And in Elm, there's really only one that you would use, which can be an advantage. But the big advantage is that Elm's package management system has very good versioning. So because Elm is type safe, if you break the API of your package, you have to bump the version number. So that makes it very easy to incorporate other people's packages and feel safe that it's going to work, right? So integration becomes very easy. So I think that's where Elm wins out, is the confidence in which you integrate other people's packages, even though there are fewer of them. And just by the nature of, what sort of open source tackles first, they usually tackle the known problems first. So with Elm, most of your standard problems are already solved by packages that you can get. Now, there are probably some corner cases out there that the React ecosystem has already solved, but most of the things that you're going to need to do to get your standard application going can be done. And then Elm also has a decent way to interop with JavaScript, or native JavaScript, which allows you to sort of do all the things you need to that aren't within the Elm framework. So we built our first beta fan experience web app was built in Elm, and it's a video-based player. So if you've ever dealt with video and React, you know that the video and sort of functional programming frameworks are not very cooperative, right? Because video is just always mutating when you play it. So the fact that we were able to build it in Elm, I think, shows that at least one of the harder use cases for web apps is possible in Elm.
So we've once again drilled down into a specific area of engineering. I think it's worth popping out even higher level to draw to a close, because we're running up against time, because Second Spectrum is quite an interesting company. I mean, I recommend anybody who's not familiar with the company check out some of the videos. It's some pretty insane data visualization and insights that you're drawing from video. Give me a picture for some of the crazier ways that data could impact sports, and give me a perspective for what's in the future for Second Spectrum.
Yeah, I think, we're just at the tip of the iceberg in terms of how data as an enabler changes sports entirely, right? And when I say data as an enabler, it's because data is what allowing today a computer to know everything about the sport, right? A particular game, the computer basically knows everything about it. And I think as we look into the future, that's really going to change the way everyone is able to, watch a game. Right now, what we've really proven out in the last 4 years is that no matter who it is in a team's organization, whether a coach, an assistant coach, a video coordinator, someone in the front office, an analyst, even the players themselves, that computer understanding of the game is able to deliver a unique set of content, a unique experience for each and every one of those people to get them what they want, right? To get them what they want in the easiest way possible, because the computer knows everything about the video and is able to surface the pieces of video or the pieces of data that a particular person cares about. Now, what we're doing now is basically taking that point of view and applying it to, fans worldwide, right? So, everyone is different, but today when you look at a game, you sit down on your sofa to watch the Super Bowl, 100 million people around the country are getting the exact same experience. Now, I would gather that not 100 million people are identical carbon copies of each other. Like, everyone would rather see it, slightly differently, personalized in themselves in their own particular way. Some people have favorite players. Some people have just, they're more technical. They've played the game themselves before, or they're very casual and they really just want to have a good time with their friends and like share funny GIFs and things like that. And so everyone has a different take on what that viewing experience should be. And basically, we've shown that we can take that computer understanding to give all the different coaches and front office staff the particular thing that they want. Now what we want to do is do the same thing for fans, right? So next year, we're going to be piloting with the Los Angeles Clippers, essentially live streaming for all of the Clippers games, where each individual fan that logs into this new service is going to get a view of the game that's custom tailored to them. Like, so if they've played basketball before, they're going to get a much more in-depth view of the game with augmentations on top of the video that really speak to them. If there's someone who's like a kid, they're going to get fun things, and they're going to be able to look at the game, through the lens of, something cute and fun and something that they can relate to, and maybe teaches them something about the game, right? And so depending on the audience, everyone can get something different now that, there's essentially a one-to-one pipe, the internet, to each and every person, and something on the other end, which is able to scale so that 1 million people can get 1 million different experiences, right? I often like to say that, this was just impossible for someone like ESPN to pull off, because ESPN cannot hire 1 million different producers to produce 1 million different shows for 1 million different fans. But all of a sudden, because, we're up in the cloud, we have computers doing all this, we can actually do that, right? So 1 million different fans can have 1 million different experiences completely tailored to them. And so that's really the future that we're trying to build right now.
That's incredible. Guys, thanks for coming on Software Engineering Daily. It's been a real pleasure talking to you about Second Spectrum and the future of sports analytics.
Thank you. It's been fun.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/SEDaily. That's symphono.com/SEDaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!